So
Yeah?
do it on your own one.
Right, okay, so the first thing when we're doing Dijkstra is we set up our open set. Okay, so I'm just going to write down all the nodes. Where's it go? Okay. And I'm going to put my costs in. Now I'm starting at C, so my travel cost is going to be 0. All the others, we set them to infinity. Now, it's very important that when you're doing this and you update things, you do not scribble things out. We want to make it clear to the example when they look at our answer that things have changed. Not that we've made a mistake, that we've updated things. But I'm going to show you something else that you can write in order to put the log of how you went through the process. So that's our starting point. We also need to keep track of the parents. So that's our cost, that's our parents. Remember, hey, A star calls it the G cost, because it has to, because there's 3 different costs. So we have to come up with letters. In Dijkstra, it's just cost. Okay. Right, the process is simple. We keep performing the iteration of Dijkstra until we run into the end node, which in our case is H. Okay, so when we visit, that's not when we explore neighbours, when we actually select that node to process, we can stop. Don't get confused with travelling salesman, which visits all the nodes. Dijkstra will not attempt to visit all the nodes if it's made it to the goal. Okay? So we'll stop as soon as time goes. Right, so we start the process, and the process is look at the costs that are available, pick the cheapest. So we look at the costs, C, because we prepped it, because it's our start, we say that's the cheapest. The first thing we do, we then say that is now unavailable, that is now closed. We do not want to select it again. If we don't do that, then we're going to end up like ping-ponging around this graph forever, like a dodgy packet of data on the internet. So we've immediately closed it off. We then explore neighbours. So C has got a neighbour A, D, F and G. Doesn't matter what order you're doing, we're just going to work out how much it would cost us to get to those neighbours. And then update the cost. So let's have a look at A, it says 1. We've got a cost of 0, so we always add our cost, the node we're visiting, to the cost to get to the neighbour. This is the bit I would like you to get used to doing though. We're going to write down that process. So we have selected C. Okay, but we're going to update A, D, F and G. So I'm telling the exam board that they are the neighbours I'm going to investigate. I'm not going to put the numbers in because the numbers are going to be up here, so I'm not going to like duplicate myself. So to A, it is 1 plus 0. So we're going to put a 1. Important to put the parent. So the parent, how I got to there with that cost was from B. So each one of these that I'm updating is going to be B initially, because I'm overwriting infinite.
C. You went from C.
Oh. Yeah. Okay. Now, if I distract myself in the exam, because I've written this down, I know I'm working from C. So that mistake I've just made, I could have double checked myself and said, oh, C, doing it from C. Okay. So please, it's like a double check of yourself. Right, so the next one was D. Right, D looks quite an expensive route. So 0 plus 10 is 10. So that again, that was from C. Next one is F. That's 7. Now we're only updating these because these costs are cheaper, which is why we force those infinities in. So that the initial time we examine a neighbour, they're always going to have a cost updated. So to get to F, that was 7. So 0 plus 7. And then my final one was G. That's going to cost me 4. So I'm going to update that. Okay. Right. That's the end of my loop, and I just do that process again. So I'm going to go for the cheapest cost. So looking at it, obviously A is the cheapest in the open list. So I'm going to select it. So I'm going to select A. It has got neighbours. It's got a neighbour B and a neighbour C. But the crucial bit, and the reason we've got this closed off bit, any that are closed, just ignore. We've visited those, we're not going to go back. Otherwise it'll end up back in the open set ready for searching, and we don't want to do that. So we're only going to examine B. Although B is infinite, so we can say we're definitely going to update B. So let's have a look. So it's taken us 1 to get to A. B is a further 4, so that's going to be 5. And that was from A. End of my loop, do it all again. So looking through, I've got a 5, 10, 7 and 4. G is going to be the next one. This is where you were like, oh, hang on a minute. But it is the next one to explore. So we're going to explore G. So we're going to close it off, let the examiner know that that's what we're doing. G's got 2 neighbours. C, which is closed, so we can just ignore it, and I. So we're going to update I, because we've not had a look at that neighbour. You can see we haven't because it's still on infinity. So we're going to cross that through because the cost is going to be better. So to get to G was 4. It's a further 3 to get to I. So we got a 7. But the parent is G. No more to do. Let's go around the loop again. So we've got a 5, 10, a 7 and a 7. So we're going to pick the B. So we close it off straight away. Write that down. So select B. Now then, B's got the neighbour A, D and E. A's closed, so we're not going to bother with that one. D is in the open set. We've got a cost already, but we need to work it out, see if we've found a cheaper way of getting to D. So let's do D first. So B's cost us 5. It's a further 4 to get to D. The cost we already got was 10, so we've now found a cheaper route. So we're going to cross that through, put the 9 on there, and we're going to say, right, well the parent, again, cross it through. It is cheaper to get to D via B. That's what that says. So we've updated D, and we need to look at E. E has got an infinity, so it's going to update, because we haven't looked at it as a neighbour yet. It's not been seen. So B was 5, further 3, so it cost me 8 in total to get to E. Know the neighbours, let's go again. So we've now got 9, 8, 7, 7. 2 with 7. Which one do we pick? It doesn't really matter. Okay? We'll just pick the first one we saw. If you pick the last one you saw, that's fine. You have no other information to go on. Dijkstra is agnostic. Okay? It only knows about the weights between the different nodes. That's all it knows. So that's all you can go on. Not the same with A star. A star has to do something different. It can actually make some logical decision. So I'm going to just pick the F because that was the first one I saw. So I'm going to select it, which means I close it off straight away. Right, F. F has got the neighbour C, H and I. C is closed. H hasn't been visited, so we're definitely going to update that one. And the other one is I, which has been seen, but we'll need to work out whether it's going to be cheaper. So let's do the I one first. So to get from F, F cost us 7. It's a further 4, so that's going to be 11. So looking at the cost of I, that isn't better, is it? Okay, so we'll leave it as is. It's cheaper to get there from G. Okay, so I, we're just going to leave. Right, let's do the update for H. This looks expensive. So to get to F's cost me 7, a further 13 to get to H. So update. Now we know that's the goal, but we haven't visited it. What we've done is we've had a look. We've had a look from afar and said, oh look, that's far away. So to get there is 20. If they've done this sensibly, they will have a graph where you have to update the weight on your cost calculations. I would have thought, so that you've shown that that's what you do. Okay, so that was from, I can't remember what node I was at, but if I look back at this, I can see that was F. Okay. Right, go again. So we've got 9, 8, 7 and 20. Right, so we're picking the other 7 now, so I'm going to pick I. Close it. Select I. I has got a neighbour G. G's gone, it's closed, so I'm going to ignore that. It's got a neighbour F. F's closed, we've been there, visited that one. So it's got another neighbour K. So we're going to update K. K hasn't been visited or looked at. It's got an infinity there. So I'm just going to tell the example I'm updating K. So the cost of K is a further 1. So it's cost me 7 so far. So that's going to be 8. And that was from I. Okay, that looks promising. From looking at it, we've got some small numbers there. But I don't know. I can't prejudge it. I haven't got anywhere around yet. No more to update, so I'm going to go and look through my list again. So I've got a 9, an 8, and an 8. Oh, I've got 2 8s. But I'm going to pick the first one. So I'm going to go with this one. So I'm going to select E. E has got a neighbour B. Closed, so we can ignore it. It's got a neighbour H, which is open, so we need to investigate that one. And it's got a neighbour J that we haven't seen. So let's update J. It's infinite, so it's definitely going to update, so I'm going to cross that out. To get to E's cost me 8, to J is a further 2, so that's 10. So that was from E. Right, let's have a look at H. So it's cost me 8, a further 12, so that's 20. That is not better. Okay, so I'm not going to bother updating it. I could if I wanted to, because it's the same cost. There's another route. It does not matter. They could be more than one optimal route.
There is.
Okay, and that really, that's what the table and the graph is showing me. So there may be more than one solution depending on the order that you pick things. All right, that's, you know, you're not guaranteed to be one route. Depends what the graph looks like. So I'm just not going to update that. So I'm going to leave H because it wasn't a better cost. It's the same cost. Amazing, I made these numbers on, it's working quite well. There you go. Right, so I'm just going to double check myself. Make sure I've been closing things off. So I should have closed off E, yeah, I, F, B, G, A, and C. They're all closed. Just double check yourself. Right, so we're going to go through that process again. So we've got a 9, a 20, a 10 and an 8. I'm going to pick the 8, obviously, so I'm going to go with K. So I'm going to select K. Right, looking at K, it's got a neighbour I, which is closed. It's got a neighbour J that's been visited as a neighbour, but we haven't been there, it's still open. So we'll have to do a costies. So looking at, it's a further 2 from whatever K cost me. K cost me 8. So that's 10. J's cost me 10. So again, it's another situation where it isn't better, so I'm going to leave it. So I'm going to leave J as it is. No more neighbours to explore. So let's go through the process again. So we've got a 9, a 20 and a 10. So I'm obviously going to pick the 9. So I'm going to select D. D has got a neighbour C, which is closed. It's got a neighbour B, which is closed. It's got a neighbour H, which is open. So let's have a look and see what the cost is going to be. So to get from D to H is 15. That looks expensive. D's already cost me 9, so that's 24. That's not better. So we're going to leave that alone. Leave H. Didn't do anything. So we've been there. Close it off. It's not a viable route. Run through again. We're running out of things to search in the open set. We've only actually got 2 now, so we've got a 20 and a 10, so we're going to pick J. So we're going to select J. J has got K as a neighbour, but that's closed. It's got E as a neighbour, but that's closed. It's got H as a neighbour. That is still open. Okay. Right, so let's have a look at that. So it cost me 4. How much did it cost me to get to J? 10. So that's 14. 14's better. So I'm going to put 14, and the new parent will be J. So I've updated H. We still haven't visited the end node, have we?
We're about to.
We're about to, because there's only one thing left. Not much of a search if there's only one item. So we're going to pick H. Close it off. Try and do that process. If you ever look in the algorithms up, the sensible algorithms will automatically say, as soon as you select something, remove it from the open set, add it to the closed set. Okay, you can implement that loads of ways. You don't have to use sets. You could use lists that you keep in order, or you could put markers saying if you've got like an object definition, you could have like open, closed, or something, a boolean that says well I'm in the open set. Right, we have actually selected and visited the end node, so we're going to stop. We've found our goal. Now that we've found the goal, we need to trace back through the parents, okay? And we'll magically have the root. So if we put that down to start with, H, where did H come from? Which is why it's called a parent. Where did I come from? All right? Which is quite amusing if you're inclined that way. Find stupid jokes. That's the definition of a computer scientist. You find really lame jokes funny. Right, so H came from J. Where did J come from? So we've got to look across. If you've cocked the parent up or forgot to put the parent in, this is going to break it. This is the breaking point. Right, E. Where did E come from? B. Where did B come from? A. Where did A come from? C. Now, if I look at C, it's got no parent, so it must have been the start point. So I don't need to go back any further. So that is an optimal solution for that graph.
There is another.
Right.
If you go along the bottom, I found that one, but we realised if you go along the bottom from C, G, I, K, J, H, it's exactly the same weights, but in a different order.
Yeah, and that has been caused by us deciding only to update if it was smaller. If it was the same, we didn't. So if we'd have actually made that decision on any, and there were a couple of times, wasn't it? If on any of those times when we had the same cost, we'd have gone, oh, well, let's just put that down. It won't break anything, and you will still find an optimal route. If later on it gets updated, it would have got updated anyway, with something better. Okay? So, in general, there will be one route, because that was just magic that I came up with one that had more than one optimal route. Pure magic, then numbers come out my head. Okay? But actually quite a nice little demo. The key thing for me is that this is clear, and then you've got this record. Because when they're marking it, they'll want to see the process you've gone through, and you'll get marks for process. Anybody could visually work out that route. Yeah, you could just look at it for a bit and add it up in no sort of algorithmic way. So the key is they're testing that you can do the Dijkstra. When you do the A star, it's the same process. You've just got more columns to worry about. Okay? Right, I'll stop that there.